All right. Good morning. Good morning to everyone who's joining in the lesson today. Guys, we are going to actually get cracking with GEC because if we are actually looking at the exam timetable for this year, most people, you guys are writing at the beginning of November. Some of you may be writing a bit early from your schools. So that means that we can't afford to be wasting time. As far as the syllabus is concerned for grade 9, I will, in due course, update the lessons on other topics. But so far, if you go to my YouTube channel, I've actually done transformation geometry. I've done a bit of surface area volume related topics, and also area and perimeter. So the concepts have kind of like been done foundationally. And so what I'll be doing is I'll be updating that as time goes by. But for the mornings, I will actually be devoting the mornings doing past GEC papers so that we can get into the routine or the know-how as to how to answer questions that are GEC related. Because those who will be writing GEC, that's if you are in a GEC type school, that will actually be, a lot of multiple choice questions. But we need to actually get into the groove of how to answer GEC questions, because I think most people will fall into a big trap, like most students have fallen into the big trap in previous years, of basically answering and multiple choice questions by simply writing in the letter and not really considering the concept behind the questions that are being asked. Because when you answer these questions, you need to actually do working out on the side and then answer those questions. Okay, so in as much as obviously this content is grade 9, but also remember that it is relevant to your grade 8 students. Your grade 8 students are also doing the same content in grade 9. But of course, when I do questions that are grade 9 related only, I will indicate that in the question when I answer it. So for instance, let's look at the question that is in front of you, section A. Question 1. What kind of a number is the square root of 5? Now, that is a question that can be asked to a grade 9 learner. Not so much to a grade 8 learner, because grade 8s only learn about numbers insofar as your natural number, whole number, and your integers. Rational and irrational numbers is only something that learners get into in grade 9 if they are doing grade 9 with the CAPS sort of like syllabus. Of course, if you are doing IEB, then that's a different story. But for a grade 9 departmental learner, then basically that is something you need to know. So if I can ask you guys in the comment section, please use the comment section and answer. You can answer with the correct letter. What kind of a number is the square root of 5? Question 1. Okay, now even though it's 1 mark, guys, remember that you need to still think, apply your thought and your thinking process. Okay, so if you look at A, do we all understand what a natural number is? Hopefully by definition, we all understand what a natural number is. A natural number is a number that starts at 1, increases by 1 all the way to infinity. So a natural number would be like a number like 1. You start at 1, obviously. And if you are increasing by 1, that means from 1 you move to 2. From 2 you move to 3, and so it goes. So all of those numbers, all the way to infinity. Remember, infinity just indicates that numbers go on forever and ever in the positive direction from 1. Okay, increasing by 1. So natural numbers are those kinds of numbers. So A can't be the answer, because the square root of 5 is not a natural number. Even if you take your calculator and you say the square root of 5, and then you press ST in your scientific calculator, when you press ST, it changes your square root number into a decimal number, and the decimal number that you get is not a natural number. So we quickly rule out the idea that square root of 5 is a natural number. So this is what I mean by when you're doing these questions, you need to actually really look at the options, and in your mind you need to be able to say, okay, square root of 5 can't be a natural number. Why? Because a natural number is a number that starts at 1. So you need to have that knowledge. So A is ruled out. What about B? What is a whole number, guys? Anyone know what a whole number is? A whole number is a number that starts at 0. So these are numbers. This is a family of numbers that start at 0. They increase by 1 all the way to infinity. So for instance, whole numbers will start at 0, 0, then we move to 1, then we move to 2, then we move to 3, and so it goes all the way to infinity. So those are the family of whole numbers. So is square root of 5 following into that family? No ways. It's an outsider. Square root of 5 is not a family of whole numbers. It's not in the family of natural numbers as well. What about C? A rational number. Now, by definition, guys, what is a rational number? I want to remind us that, guys, a rational number, okay, if we remember very clearly, I'm just going to remove this. So, and a rational number is a number. This number can be expressed. It can be expressed as a fraction. Okay, and generally speaking, we can say A over B. Now, A in the numerator must be a integer. Now, that's another concept we need to understand. This Z means integer. What are integers? Integers are numbers that are positive and negative. In other words, if you are listing numbers from negative infinity, negative 1, 0, 1, 2, and so it goes to positive infinity. So these are positive and negative whole numbers. Those are integers. So your numerator number must be an integer in order for it to qualify as a rational number, and your denominator number as well. B is an element of integers. Your denominator number also must be an integer. All right, so as long as that is the case, and B must not be 0. All right, so if you have a fraction where the numerator and the denominator are both integers, and B is not 0, because remember, if B is 0, what happens? If B is 0, it means the fraction is no longer rational. It means the fraction or that number is undefined if we have a 0 in the denominator. So going back to what I was saying earlier on, can square root of 5, oh, here's another thing as well about rational numbers. Under a even root, so in other words, if we have a square root, then in order for this number to be termed as rational, then the number under the square root needs to be a perfect square number. In order for the number under a square root, remember a square root is an even root, all right? In order for that number to be called a rational number, it needs to be a perfect square number that is under the square root. Okay, so under a even square root, then of course we need to have a perfect square number. If it is a cube root, then we need to have a cubic number. Okay, if it is a fourth root, then we must have a number that basically will result in a natural number if it is placed under that fourth root. So for example, guys, if it's a square root, square root of 25 will give us 5. That's why we can say 5, because 5 can be written as 5 over 1, is a rational number. Cube root of 8 is also going to be a rational number. Why? Because 8 under a cube root is a cubic number. It's cubic. The cube root of 8 gives us 2. 2 can be written as 2 over 1. So that is why we are saying that as long as the number under that particular root is actually going to result in a natural number, then we say that that particular number is a what? Is a rational number. So if it's a square root, then it must be a perfect square number under the square root. If it's a cube root, then it must be a cubic number under the cubic root in order for it to qualify as a what? As a rational number. I hope that makes sense, guys. So rational numbers, like I said, can be written in the form of a fraction, where the numerator and the denominator are integers, and where the denominator can never be 0. Then also, remember, if b so happens to be 0 in the denominator, then we know that that particular number is what? Is undefined. We say undefined, guys. Then also, if we have a square root, then we know that if we are to have this as a rational number, there must be a perfect square number underneath the square root. If we have a cubic root, then it must be a cubic number under the cube root. Like, for instance, if we have the square root of 25, this square root, in order for it to qualify as a rational number, must have a perfect square number under the square root. Hence, the square root of 25 is 5, and 5 can be written as 5 over 1, which is a rational number. This is an integer. This is an integer. The cube root of 8 results in 2. Remember, under the cube root, we said we need to have a cubic number under the cube root in order for it to qualify as a rational number. Therefore, we say that the cube root of 8 is what? It is 2. All right. And so the same logic follows. So that is why I recommend that whenever you are given something, put it in your calculator. Then you should be, if you get a number that can be written in the form of a fraction where the numerator and the denominator are both integers, then you can clearly rule it as a rational number. Very, very important for you to be able to grasp that mindset. Now, I want to speak about the decimals of a rational number. So if you look at the decimals of a rational number, it falls under this camp. We have recurring decimals. Okay? By recurring decimals, guys, we mean this. 0.3. Let's say we put a dot on top of the 3. What does this mean? This means your 3 repeats infinitely. That's what it means. This recurring decimal is an example of a rational number, because this 0.333 can be written as 1 over 3. And there is a way to convert decimals that are recurring into rational fractions or rational numbers like this, where the numerator and the denominator are both integers. Let's look at another example. 0.57. Let's say they put a line like this, or they put a dot like that. Both of these guys mean that 0.57 repeats itself infinitely. 0.57, whether there's a line above the two numbers, it means 57 repeats infinitely. This can also be converted into a particular fraction. You guys should have learned how to convert a particular repetition of 2 digits after the comma into a rational fraction. Remember that a line above numbers or dots above numbers indicates repetition. Those are what we call recurring decimals. Recurring decimals are rational numbers because they can be written as fractions where the numerator and the denominator are what? Are integers. So that's one camp that rational number decimals fall under, recurring decimals. 2, terminating decimals. Terminating decimals. What does terminating decimals? So you should know the movie The Terminator. The Terminator is a movie where we see this guy, Arnold Schwarzenegger. There's a killing spree that happens there. End of life. To terminate something, even to terminate a pregnancy. Please guys, hopefully none of us are thinking of even having such a situation. Termination, aborting a baby. But termination, terminate. The word terminate means to come to an end. So for instance, if we have 0.2, what you see here is that this decimal number, after the comma, the number does not repeat, nor are there other numbers that are going on forever. This number is the only number. So we come to a stop after the first decimal. So after the first decimal, meaning there's a rounding off to the first decimal here, which means 0.2 is what we call a terminating decimal. This can be written as a what? As a fraction 2/10, which can be simplified to a fraction 1/5. This is another example of a rational number. 0.1872. Once again, 1, 2, 3, we are stopping at the fourth decimal. As long as some decimal place we stop, we call these kinds of numbers terminating decimals. All terminating decimals are what? They are rational numbers. So guys, I hope with this said, you guys are getting a deeper understanding of what we mean by a rational number. You need to understand this so that you can be able to identify a rational number when given one. So going back to my question section A, number 1. What kind of a number is square root 5? We can clearly see that A, it's not a rational number. It's not a natural number. Why? Natural numbers are numbers that start at 1, increase by 1 all the way to infinity. So it's not a natural number. B, is it a whole number? No, it's not a whole number, because whole numbers are numbers that actually start at 0 and increase by 1 all the way to infinity. So B is out. C, is it a rational number? Guys, under what I've just explained, I've explained that a rational number, guys, we've explained it now, that a rational number is a number that can be expressed as a fraction, where the numerator A over the denominator B have to both be integers. What are integers? These are positive and negative whole numbers that increase by 1. So from 0 they increase by 1, and from 0 they decrease by 1. So 0, 1, 2, 3, 0, negative 1, negative 2, negative 3, these are integers. So as long as the numerator and the denominator are both integers, and the denominator can never be 0, then we know that this is a rational number. Okay? We know that when B is 0, meaning the denominator is 0, then we know that the fraction is not a rational number, but it is undefined. Then we spoke about how rational numbers are represented in a square root. If it's a square root, then there must be a perfect square number underneath the square root. If it's a cube root, then there must be a cubic number under the cube root. And examples that I've just mentioned here, if you look at the square root of 25, this is a perfect square number under a square root, so therefore the answer is 5. The answer is 5/1. This is typically a rational number. The cube root of 8, under the cube root, there is a cubic number, 8, because 8 can be written as 2 times 2 times 2. That's why we say 8 is a cubic number, because it can be written as a multiplication of these 3 numbers, 2 times 2 times 2. So 8 is a cubic number. What about 25? 25, we say, is a perfect square. Why? Because it can be written as a product of itself, 5 times 5. All right? So that's why we say 25 is a perfect square number. Okay? Yeah. So guys, I hope this is so clear for us that rational numbers, okay, if it's a square root, then underneath the square root there must be a perfect square number. If it's a cube root, then there must be a cubic number under the cube root. If it's a fourth root, then obviously there must be that kind of number that can be multiplied by itself 4 times underneath that fourth root in order for it to qualify as a rational number. If it's a fifth root, there must be that number underneath the fifth root that can be multiplied by itself 5 times in order for it to actually qualify as a rational number. Then for decimals, guys, how do we identify in decimals rational numbers? Decimals fall under 2 camps for rational numbers. We can either have recurring decimals. Okay, by recurring we mean, the word recur means to repeat. What is repeating? The number after the comma. So 0.3, if there's a dot on the top, it means 333 repeats itself indefinitely. And you can see the dot is just to indicate that this 3 is going on forever. 0.57. And on top of the 0.57, if you have a line on top, this also means a repeat. So a dot and a line are the 2 symbols that stand for repeat or recur. All right? And these all fall under rational numbers. Then lastly, terminating decimals. They also fall under rational numbers. How do I identify terminating decimals? After the comma, if the number is stopping at a particular decimal place, then we say it's a terminating decimal. This 0.2, first decimal place, it's rounding it off to two first decimal place. It means this is a terminating decimal, and it can be written as a fraction 2/10, which is 1/5 when simplified. 0.1872 stops at the 4th decimal place. The 4th decimal place, we stop, we terminate. Terminate means to stop, to terminate a pregnancy, to terminate a contract, termination of employment. Terminate means to stop. Where are we stopping? At the 4th decimal place, we are terminating the decimal. That's a rational number. Where do we stop? At the 1st decimal place, we are terminating the decimal. We say this is a rational number as well. It qualifies as such. Then lastly, irrational numbers. What is the thing about irrational numbers? Guys, irrational numbers are simply 1. Under the square root, it's not a perfect square that you see. For instance, the square root of 3. 3 is not a perfect square number. Therefore, underneath the square root, we know that this here will be irrational. Okay, irrational. Underneath the cube root, obviously we have a non-cubic number. Underneath any other root, we have a number that basically indicates that the number is irrational. And therefore, what further confirms the fact that irrational numbers are irrational numbers is when we see that the decimals are non-recurring and non-terminating. What does non-recurring mean? It means there is no repeat of numbers, no pattern or repeat of patterns. I will show you an example, guys, by this. For instance, if I write down the square root of 2, the square root of 2, guys, look at it. It gives me 1,414,213,562,37. This is the square root of 2. Now, we say that this is a non-recurring decimal. Why do we say non-recurring? It's because there is no pattern of repetition. Okay? There is no pattern of repetition. 4, 1, 4, 2, what a change. 1, 3, I change. 5, 6, no pattern. No pattern of repetition at all. 2, we say it is also non-terminating. So it's both non-recurring and non-terminating. Those are irrational numbers. Why do we say this is non-recurring? Because there's no repetition. Why do we say this is non-terminating? Guys, this here is the calculator interface. But if our calculator was extended further, you would see that there's other numbers that are following. But it's just that because our calculator only has these number of decimal, it only ends at this decimal place. Trust me, if the calculator was a bit more open, you would see other numbers that are not repeating, that are continuing. That's why we say that an irrational number is non-recurring and it is non-terminating. Okay, so that's irrational. So now I bring back the question, guys. What kind of a number is the square root of 5? A, is it a natural number? B, is it a whole number? C, is it a rational number? D, is it an irrational number? Based on what I've explained about A, B, C, and D, what can you say is the answer to this question? What kind of a number is the square root of 5? Is it A, a natural number? Remember, natural numbers are numbers that start at 1, increase by 1 all the way to infinity, so it's not that. B, a whole number. Remember, whole numbers are numbers that start at 0, increase by 1 all the way to infinity. It's not that. C, a rational number. Square root of 5. If you write square root of 5 as a fraction, it's square root of 5 over 1. Is square root of 5 in the numerator an integer? No ways. Okay, even though 1 in the denominator is an integer, but the numerator is not an integer. So therefore, we would have to say, if we take that square root of 5 and punch it in the calculator, this is what I like doing personally. You know, when all else fails, I like punching in the question, the particular thing in the calculator. So let's punch in square root of 5. Look at that. What do we see? 2.23606797775. What is this reminding you of? When you look at the decimal number, the square root of 5 has been put into my calculator. I can confirm using my calculator what kind of number this is. Very clear, guys, that 236, no repetition, 06, no repetition, no pattern of repetition. And it is non-recurring and non-what? Terminating. We know that this would go on forever. It's just that we don't have enough calculator space. So this is definitely D. It is definitely D, guys. An irrational number. Okay. Please, grade 9s, make it a point that you know your content. So just from question 1, I now have been able to revise my numbers. You know, I was able to revise all my numbers just from that question because I took the time to check A, natural number, what is it again? Whole number, what is it again? C, rational number, what is it again? And then D, an irrational number, what is it again? Then I was able to make the most correct choice. Let's go to number 2. What is the LCM of 14 and 16? The question says, what is the LCM of what? Of 14 and who? And 16. Okay, now this is a grade 8 question. Can be asked to a grade 8 learner, and it's also relevant for a grade 9 learner. Now you should have learned methods on how to find the LCM. What do we mean by LCM? We mean lowest common multiple. Lowest common multiple. And as grade 8 and 9 learners, you should have all been exposed to what we refer to as the tree diagram or the ladder method on how to find the LCM. Okay, so I'm just going to expose us to that. If we write down the number 14 and 16 and then we find the prime factors. What do we mean by prime factors? Remember, a prime number is a number that has 2 factors, 1 and itself. So if you think about numbers in your number system between 1 and 10 that are prime numbers, prime number, like I said, is a number that has two factors, 1 and itself. So between 1 and 10, what are the prime numbers that you know? 1 is not a prime number, guys. 1 is not a prime number. Don't ever make that mistake of saying 1 is a prime number. What about 2? Yes, it is, because the factors of 2 are 1 and 2. 1 and itself. What about 3? 3 is a prime number because the factors of 3 are 1 and 3. So it is. What about 4? Well, 4 is not a prime number because the factors of 4 are 1, there's 2. 1 goes with 4, 2 goes with itself 2. There are 3 factors. So 4 is not a prime number, but rather we call this a composite number. What is a composite number? A number that has more than 2 factors. That is a composite number. A number that has more than 2 factors. So you see, just from this summary, I am learning things that I have forgotten. Prime factor is a prime number, is a number that has 2 factors. So what is a prime factor? A prime factor is simply a number that will have these conditions. A number that will have either 1 or itself as a factor. So between 1 and 10, we know 2, we know 3, we know 5, we know 7, and that's about it between 1 and 10. Because 1 is not a prime number, 2 is, 3 is, 4 is not, it's a composite number. 5 is a prime number, 6 is not, it's a composite. 7 is a prime number. 8 is not, it's a composite number. 9 is not, it's a composite number. 10 is not, it's a composite number. So these are the prime factors. Right? These are what we call prime numbers, which can then be known as prime factors. So if we are looking here and we are wanting to find the prime factors of 14, the first and lowest prime factor of 14 that goes into 14, because factors are numbers that go into another number without leaving a remainder. These are numbers, factors are numbers that go into another number without leaving a remainder. So we want to find specifically the numbers that are prime that go into 14 without leaving a remainder. So let's look at the lowest prime number that can go into 14. What is it? Okay, I believe we all know it is the number 2. How many times does 2 go into 14? That number we are going to write down here. 2 goes into 14 how many times? 7 times. Then we look at this number 7 and we ask ourselves the very same question. What is the lowest prime number that goes into 7? Now 2 obviously doesn't go in, it's not a factor. Okay, because 2 will go in 3 times, but then it will leave a remainder of 1. So we can't write that as a prime factor that goes into 7. So let's look at another one. What about 3? No, it doesn't. 5 doesn't. 7, yes it does. 7 is the next smallest prime number that goes into 7. Okay, so therefore that means 7 goes into 7 how many times? Once. Once we get here, guys, we know that we have finished our ladder. Therefore we can say 14 can be written as 2 times 7. This here, guys, are what we call the product multiply of prime factors that will give us 14. Let us go to 16 and do the same thing. What is the lowest prime number that goes into 16? It's 2. How many times does it go into 16? 8 times. Smallest prime number that goes into 8? 2. How many times does it go into 8? 4 times. Smallest prime number that goes into 4? 2. How many times does it go into 4? 2 times. Smallest prime number that goes into 2? 2. How many times does it go into 2? Once. Once we get to 1, we stop. Then we write down 16 is equal to, how many times do we have 2? 2 times 2 times 2 times 2. But then we can express this product of prime factors. Since it's 2 by itself, we can say 2. How many 2's do we have? 1, 2, 3, 4. So we write the exponent 4, which is an indication of how many 2's do we have? 4. How many 2's do we have? 4. How many 2's do we have? 4. Exponent, base. How many 2's do we have? 4. Exponent indicates how many 2's we have. 2, our base, which is basically the number that is repeated, which you see there. That's why we write this 16 as 2 to the power 4. This is the exponential form of our number 16, 2 to the power 4. So now we can say 14 is equal to 2 times 7, whereas 16 is equal to 2 to the power 4, all right? And therefore, when we want to identify the LCM, we do the following. We identify the common base with the highest exponent. Common base with the highest exponent. So between 14 and 16, we are looking at base 2. We can see base 2 is common for both 14 and 16. So identify the common base. It is 2 in this case. So that means we can write down 2. But then which one will we choose? Which one between 2 and 2 to the power 4 has the highest exponent? So this one is 2 to the power 1. If we were to reveal what's there, this one is 2 to the power 4. So we are going to choose who? 2 to the power 4. Then we multiply. Now, lowest common multiple mean we identify the common base with the highest exponent. Now the thing is, if we look at 7, 7 is not common. But for LCM, we also take down the leftovers that are not common. I usually say that to my learners, the leftovers that are not common. So here, 7 is a leftover, not common. So we are going to write it there as a product as well. Okay? We include it as part of the LCM. So the LCM is equal to 2 to the power 4 times the 7. You take your calculator. This is 16 times 7. What is 16 times 7, guys? From what you guys are getting from your beautiful calculator, 16 times 7 is equal to, let's see if people are actually here and are interacting. What is 16 times 7? Because that will be my lowest common multiple, which I need to go and identify. What is the LCM? What is 16 times 7? What does that give us? 6 times 7 is 42. 7 times 1 is 7 plus 4 is 11. So it's 112. That is the LCM. If you use your calculator, you'll get the same answer, 112. Let's go to our multiple choice. What is the LCM of 14 and 16? Guys, I've just worked it out. Okay, I worked it out. Okay, now I'm sure you guys know that you can actually get the product of factors using your calculator. If you want to get the product of factors without using the ladder method, using your calculator, your scientific calculator, your Questio, your latest version, you can say 14 is equal to shift fact. You'll get 2 times 7. Then you can say, same thing here, 16 is equal to shift fact. Go to your calculator, go press it. 16 is equal to shift fact. It will give you 2 to the power 4. Then, of course, you can then write down the product of prime factors and then identify the common base with the highest exponent. And obviously, your accompanying leftover, and then your LCM is sorted. Okay. So our answer there is simple. What is the LCM of 14 and 16? It's B, 112, guys. That is the answer. Okay. Right, moving right along to number 3. Okay, that is why you guys need to bring back your content knowledge from the previous terms. As we approach the exams, revision means bring back the content from previous terms. Please, guys. Number 3, a car travels 180 kilometers in 2 hours on a straight road. How many kilometers can the car travel in 210 minutes at the same speed? Now, before we even answer this question, we are told that a car is traveling, 180 kilometers in 2 hours on a straight road. Then we are being asked now, how many kilometers can the car, guess when you're talking about the same car, can the car travel in 210 minutes at the same speed? So this is a nice question, right? And depending on who's doing the question, a person can either look at this question and think of, and I'm hoping you guys are thinking of this, DST. DST. D stands for distance, S stands for speed, and T stands for time. So this is under the topic rate. Remember, rate is the comparison of 2 or more quantities, that have different units. That's what rate is, grade 9s. So we can then say distance is equal to speed times time. We know distance. S and T are next to each other, product of each other. S is equal to, you hide S, D over T, if you wanted to calculate speed, and then T, hide that, is equal to D over S. So it's good to know this diagram, so that you are able to actually do calculations. So you can look at this in terms of rate, or if you are someone else, you can look at this in terms of proportion, direct or indirect proportion, because if you are a learner, there are 2 ways that you could find the answer for this question under the syllabus that we are in. So I'm going to look at this a bit later. Let's look at how to approach this question using distance, speed, time, which is a rate. So a car travels 180 kilometers in how long? In 2 hours. What is this? Car travels 180 kilometers. What is this? This is distance. In 2 hours, this is time. How many kilometers does the car travel in 210 minutes at the same speed? So what do we want to first do? We want to first calculate the speed that this car is traveling initially. So a car travels 180 kilometers in 2 hours. So let's go ahead and say S is equal to D over T. Do we have distance? Yes, we do. It's 180 kilometers. Do we have time? Yes, we do. It is 2 hours. Let's look at the units. Very important that the units need to complement each other. If distance is in kilometers, then it must be that time must be in hours, because kilometers per hour, kilometers and hours go hand in hand. But if we had minutes, if we had other alternative units, we would have to change the units to the correct units. Please, guys, very important, this thing. So kilometers and hours, they go hand in hand. So we can go ahead and calculate this. 180 kilometers divided by 2 hours. What does that give us? For speed of the car, 180 divided by 2, we know that is 90 kilometers per what? Per hour. Okay, that's our speed. Then we can take the speed, because it is the same speed, and then it says how many kilometers in 210 minutes. Now, what does that mean? How many kilometers? It means we need to now calculate distance. So we are going to now calculate distance. We know that our speed is 90 kilometers per hour, and we have now seen that the time is 210 minutes, which means our minutes need to be converted to hours. How do we convert minutes to hours? How do we convert min to hour? How many minutes are there in 1 hour? That's the question. How do we convert minutes to hours? The question is, how many minutes are there in 1 hour? In order to be able to answer that question, we need to first answer how many minutes are there in 1 hour. Then we know there's 60 minutes in 1 hour. So we're going to take 210 and divide by 60 so that we can find out how many minutes, what is the hours when we have 210 minutes. So what is nice here, from there you can go ahead and grab your calculator. 210 divided by we get 3.5. It seems like we're getting 3.5. One person is saying in the comment section. Do we agree, guys? 210 divided by 60. Okay, thank you so much. Very good. 3.5. Right. So now we can calculate the distance, because the question is how many kilometers in 210 minutes. So let's say distance. Which formula do we use? Distance is equal to speed times time. So speed, 90 kilometers per hour. Time, 3,5. Then we use our calculator. 90 times 3,5. That will give us an answer of 315 kilometers. Okay. So if we go back, how many kilometers can a car travel in 210 minutes at the same speed? Okay. You see, we used the same speed to calculate the distance. So you can see it's 315 kilometers, guys. All right. And really and truly, you see, we need to make sure that our units are complementing each other. If we're having kilometers per hour, then it means our minutes need to be converted into hours. And it's very important that we make the conversion happen before we are able to plug into the formula, which is D is equal to S times T. S meaning speed, T meaning hours, our time, and then getting the answer 315 kilometers. So we go to our question and we can clearly choose option D. We can clearly choose option D. Okay. Yeah. I wanted to look at this in terms of direct and indirect proportion, because you can also look at it in that way. All right. I want to look at it as way, because remember, direct and indirect proportion tells us that as one quantity, for direct proportion, we are told as one quantity. Okay, I'm going to look at the same question. As one quantity increases, the other increases as well. That's for indirect. That's for direct. Or vice versa. As one quantity decreases, the other one will decrease. That's direct proportion. Indirect, on the other end, says as one quantity, as one increases, the other decreases. All right. Now, the interesting thing here is that we are told that here we are told that the ratio is constant. Okay, but here we are told that the product is constant. And these are very important things to note. So I'm going to show you guys what we mean by doing the same question. The same question can be answered not with rate approach, but with the indirect and direct proportion approach. So if we look at the same question again, it says a car travels 180 kilometers. So we are comparing two things here, distance and time. So let's look first at the car travels how many kilometers? 180. Okay, 180 kilometers in what? In 2 hours. Then now they're asking the question, how many kilometers will the same car travel in what? In 210 minutes. Our 210, we converted it most. Okay, because obviously since we are dealing with time and we would want to have the same time in the same unit, we want to have time in the same unit. So 210 minutes, we take 210, we divide by 60, we get 3,5. So 3,5 is now our time there. Okay, so when the car is traveling a distance of 180 kilometers, it's taking 2 hours. Now the question is, how much distance is it traveling to be traveling 3,5 hours? So logically speaking, I want you guys to see this. I want you to logically first apply understanding. What is happening here? As distance is 180 kilometers at 2 hours, what are we expecting here? Are we expecting the distance, since now it's 3,5, are we expecting the distance to be more? Are we expecting the distance to be less? Okay, look, when the car is traveling, when the car is traveling at 180 kilometers, when the distance is 180 kilometers, it's taking it 2 hours. So what distance will it be more than 180 for it to be traveling 3,5 hours, or will it be a distance that is less than 180? So are we expecting more, or are we expecting less in this distance? So what I want to check by doing this is that what is happening to the time, as the time increases. My question to you is, what is happening to the distance? Is it also increasing? Okay, so with 2 hours, it takes 180 kilometers. With 3,5 hours, will it take more than 180, or will it take less than 180? That's what you need to be thinking in your head. All right. So I don't know, because no one is saying anything in the comment section. And so I'm like, I don't know if people are even hearing what I'm saying here. 180 kilometers. So the distance that this car is traveling, okay, is 180 kilometers in 2 hours. So if it's taking 3,5 hours, will it be traveling more of a distance than 180, or will it be traveling less than the distance of 180? That is my question to you guys, and that's what I need you guys to answer. Okay, so if you are saying that at 3,5 hours it's traveling more of a distance, then it means that there's also an increase in the what? In the time. In the distance. So as the time increases, the distance is also increasing. That's what we are saying, right? And I think the logic we can apply here is that as the time increases, indeed the distance also does what? Increasing. So that means we are dealing here with a direct proportion situation. And what do we know about direct proportion? As one quantity increases, the other increases. So if we're moving in this direction, we are talking about an increase in distance, also an increase in time. But if we are moving in this direction, we are talking about a decrease in time, but also a decrease in distance. So this is a direct proportion situation. And under direct proportion, we know that the ratio between the quantities is constant. I repeat, the ratio between the quantities is constant. Okay, so what I can then do, or what I will do, guys, is that between the quantities, we are going to say the ratio is what? Is constant. So if I talk about between the quantities, it means I can then say 180 over 2 is equal to x over 3,5. This is my application of direct proportion. I repeat, x over 3,5 is equal to 180 divided by 2. Now the key here is to ensure that our unknown that we are looking for is always in the numerator. So we always set up our table in such a way that the x value is always in the numerator, so that it makes it easy for us to solve the equation, solve for x. Now we want to isolate x, and from our knowledge of solving equations from term 2 as grade 9 learners, we should be able to know how to solve for x for this equation. What do? We simply multiply by what is in the denominator, but we do that both sides. So the 3,5 we multiply in the numerator, 3,5 times 1, over 1. So we do the same there on this side. What does this lead to? It leads to the cancellation. X is isolated. Now you can grab your calculator and multiply this. 35 over 1 times 180 over 2. Guys, it should lead you to 315. Again, 315 kilometers. And this is how we do this question using the indirect or direct proportion. We apply our proportion concept into a question that typically most students use the rate approach. Okay? All right. But it needs our conceptual understanding first of rate and indirect and direct proportion in order to apply this information. Okay. So guys, I think we can clearly say that number 3, it is exactly D. 3D is the answer. Nothing more, nothing less. 3D. Okay, let's move on to number 4. Right. And you might be noticing that you're taking a long time to answer one question. Remember, guys, as I said, you guys, I'm teaching you at the same time, right? Bringing things to your own memory and remembrance. I'm trying to remind you of the things that you should be knowing. Okay, so that's why we are taking quite a while. Let's look at number 4. We are given an expression there. 3 brackets minus into minus 3 plus 17 brackets, then square brackets, minus into minus 4 with a bracket times 2. So in the question there, they are saying which of the following is the correct answer? A, is it 50? B, is it 46? C, is it negative 40? Or is it D, negative 34? So here, who are we applying in order to solve such a problem? We remember bad mass. We remember who? Bad mass. What does B stand for? Brackets. Okay. Brackets. E, exponents. Okay, if they are exponents, the priority exponents. D, division. M, multiplication. A, addition. S, subtraction. Okay, so we apply that here in this mathematical statement. So we look at this and we look at this and we're like, okay, there's a 3. The brackets, okay, I know brackets mean multiply. Okay, 3. These square brackets, okay, mean we are going to do that later. The small brackets get priority right now. Okay, minus times the 2. So we are going to focus on the bracket. Let's look at inside. Minus into, let's look at what's inside. What's minus 3 plus 17? That gives us 14. Okay, then we have this negative sign and this negative 4 times this 2. Okay. Right. Then still smaller nyana bracket, negative into 14, negative into 14, negative times positive, because brackets mean multiply. That's 3 into negative 14. Right. Now we can multiply as well here. Negative 4 times negative times negative 4 times the positive 2, so that we can resolve the sign that's here. Negative times a negative is a positive, positive times a positive is a positive. So this is multiplication. Remember, brackets mean multiply. So that means we get positive 8 there. Okay, so this multiplication can be done with the negative sign being multiplied by this negative 4 times this positive 2. Or you could say negative 4 times 2, which gives you negative 8. Then the negative 8 you still multiply with this negative to get a positive 8. Okay, then remember the bracket here still means multiply. It still gets the priority. 3 times negative 14, that gives us 42. Negative 42. Let's not forget, positive times a negative, negative. 3 times 14, 42. So it's negative 42 plus 8. Then what's negative 42 plus 8? Now, guys, we are can safely say that we don't have to deal with, we dealt with multiplication as it referred to us, brackets meaning multiply. Now we can deal with addition and subtraction. Negative 42 plus 8. Negative 42 plus 8, guys, gives us what? So it's negative 34. Okay, yeah. Right. So guys, just something to note here, that at the beginning I started with the small bracket. Remember that what is inside those brackets matters. It gets first priority. So even as much as brackets mean multiply, remember that brackets means that what is inside gets priority. So if you are at school and you have a feeding scheme and people have to go to the line and get fed food first, who always gets the food first? It's always the bracket. Who gets attended to first? It's always the bracket. Then who follows? The exponent. Then who follows? Then division. Then who follows? Multiplication. Then lastly, addition and subtraction. Addition and subtraction always come at the end. So if you go to your answer again, we have D. Which of the following is the correct answer? It is D. Guys, how many times have we selected D? Section A, what kind of number was square root of 5? The answer was D, an irrational number. What is the LCM of 14 and 16? We did calculate number 2. We got B. 3, a car travels 180 kilometers in 2 hours on a straight road. How many kilometers can the car travel in 210 minutes at the same speed? Using rate, DST, or using direct proportion in this case, we were able to get D, which is 315 kilometers. And then lastly, which of the following is the correct answer? We got D, which is negative 34, because we know that when we apply odd mass or bad mass, we get that answer. Okay. Isn't this fun? Don't you think? I hope so. I hope you guys feel the fun that is here. All right, let's go on to number 5. Okay, guys, we may end somewhere. We're not going to do everything that's here, but we'll end somewhere. But I hope this is really helpful. If you guys are feeling that this is really helpful and you're benefiting, please indicate in the comment section level 7. If it's not, really you're not feeling it yet, and it's really taking you some time to get into the flow of things, hopefully you can write, whatever is relevant accordingly in the comment section. And remember, I will be posting this onto my YouTube channel later on in the day. So I'm going to save the video, upload it onto the YouTube channel, and I will be continuing on with the same paper tomorrow, same time, 5:30. Try to start at 5:10. Try to start very early. Grade 9s, you need to get into the habit of waking up early to actually get into the swing of things when it comes to maths. Okay, so the earlier you get, the better. And please do share the live with friends that you may have that are in grade 9, because the more grade 9s we can get here, the more we can get everybody into the ball game of answering GEC papers. I will not only be focusing on GEC papers, of course, I'll do other papers, but I will focus really in the mornings of every single morning I'll focus on grade 9s and helping them answer question papers, so that we can get the term 1, term 2, term 3 work that we have done, which we've forgotten, back into our memory. See? Okay, so number 5, a is equal to 2 and b is equal to 3. What is the value of 3 into minus 2a plus times b plus 6a squared into b squared over ab? So we are told that a is equal to 2, b is equal to 3. Okay. The person was asking me about grade 10 and stuff. I have no working schedule for grade 10, so I'm sorry. Askis. Okay, let's look at this, guys. How do we go about doing this? So if a is equal to 2 and b is equal to 3, here we are playing the substitution game. Okay, substitute, and we use what when we substitute? When we substitute, guys, we use brackets, please. So in the place of a, you are going to substitute 2 and use brackets. So let's go 3 into minus 2 into 2 times b. Okay, b is 3. So in the place of b, we're supposed to write 3. Okay, right? Okay, so let me just rewrite this. 3 into minus 2 into 2 times 3. Okay, please, distinguish between the brackets. This is the small bracket for substitution that I've placed, because in the place of a, I'm writing 2. In the place of b, remember, we're supposed to substitute 3, followed by this plus 6 into a is 2, b is 3, over 2, 3. So once again, this is just a simplification of integers, applying BODMAS or BEDMAS if you want. Brackets, exponents, division, multiplication, addition, and subtraction. So this big bracket, I'm going to focus on what's inside so that I can resolve this and multiply it with 3. 3 is ready to be multiplied with what's inside, but we need to just resolve what's inside first. So you can maybe just get the answer, because this is multiplication all of it. So what's negative 2 times 2? That's negative 4, because a negative times a positive is a negative. Negative 2 times 2 is negative 4. Negative 4 times 3 is negative 12. So we are multiplying that negative 12 with 3. That's fine. This is a plus, which separates this here from that there. So I can treat this independently. BEDMAS. Let's apply BEDMAS here. 6 can wait. 2 squared and 3 squared. This is a bracket with an exponent. So according to BEDMAS, BE, brackets, exponents. So let's look at the order. 2 squared is 4. 3 squared is 9. Okay. 2 squared is like 2 times 2, and then 3 squared is like 3 times 3. All right. I hope that makes sense. Over. In the numerator, we have 2 times 3, which is 6. So this 3 times negative 12, positive times a negative is a negative. 3 times 12 is 36. So we have negative 36 there. Plus, what's 6 times 4, guys? 6 times 4 is 24. 24 times 9. You can use your calculator there, 24 times 9, and you can get your answer very nicely, which makes it very easy. And so that gives us 216, I believe. Please do correct me in the comment section if you guys feel like no. Okay, this is basically me doing this for you step by step so that you can see how the answer came about. Because remember, in a typical, let's say if you were answering a question paper in term 1 and you were given a question like this, you would be required to show your steps. And it is when you are able to show your steps and apply the mathematics, right? Bad maths. Okay, so you can see B being applied there. Here you can see BE being applied there, right? And then obviously brackets meaning multiply. You see? Multiply. You can see that multiplication, you know. Even here we apply the multiply. You see? Yeah. B being multiplied. Now we are multiplying the multiply. Negative 36. That's plus, which separates this from that. 6 times 4 times 9, which gives us 216 over 6. Then we can add, you know, 216 minus 36. That's priority, right? So what do we get there, guys? Is it 280? I believe. No, 180. Then 180 divided by 6. That gives us 30. Okay. Do you see how I was able to get that step by step? Okay, so here at the top, okay, I can add, but remember the line means divide. So obviously this is comparable to having a bracket, because at the top you have to deal with the numerator, get the answer for the denominator, and then you can divide the two. Okay, so 180 divided by 6 is 30. If we go back to the options, what is the value of? Is it 18? A? Is it B? 30? Is it C? 42? Is it D? 48? Clearly we can see, guys, that the answer is what? B. It's B. Okay. So now I can go and write my answer nicely because I've actually really worked it out. GEC requires such, guys. Please don't just go and circle answers for the sake of circling them. Apply the maths. Hey, and you must practice the maths first so that you can apply it. The maths cannot be applied unless practiced. Okay. Let's go to the next question there. Negative 4 to the power 3 over the square root of 4 times the cube root of 8 plus the square root of 64 over 2 minus 2 squared. What is the value in simplest form of the expression? Is it A, negative 16, B, 16, C, negative 3, D, 3? Which one is it? Okay. Beautiful question, by the way. Odd exponent applied to a negative sign leads to a negative number. An odd, this is an odd exponent applied to a negative sign leads to a negative answer. If it was an even exponent applied to a negative sign, it would lead to a positive answer. But since it's an odd exponent, this is very important, guys, that the minute you have a odd exponent applied to a negative sign, it leads to a negative sign. But if you have a even exponent applied to a negative sign, it leads to a positive answer. So this application there, negative, then what's 4 cubed? 4 cubed is 64. So we have negative 64 as the answer. Some people would use their calculator and just get negative 64, which is fine. Square root of 4 is 2 times the cube root of 8, a perfect cube under a cube root. This is 2. Okay, plus, what's the square root of 64? 8 over 2 minus, the 2 is inside, okay, the square is also inside. 2 squared is 4, negative 4. Okay, guys, do you see step by step how I'm unraveling this thing? It's like I'm opening up a present, serving you a nice present, Christmas gift. Negative 64 over what's 2 times 2? It's 4. 8 divided by 2 is 4. Minus who? Minus 4. Negative 64 divided by 4. Thank you so much, Les Williams. Such a nice rose there. What a beautiful, beautiful. Thank you so much. Then negative 64 divided by 4. Does anyone know what negative 64 divided by 4 is? Before I write the answer, negative divided by positive is negative. What's 64 divided by 4? It is 16, guys, right? Negative 64 divided by 4 is negative 16 plus 4 minus 4. I'm sure you guys can see that the answer now, applying BODMAS, is simply going to be negative 16. That will be our answer. Okay. Isn't that nice, guys? Isn't that a nice problem? Just repeat again. Odd exponent applied to a negative sign leads to a negative sign. 4 to the power 3. So you apply the exponent to the sign, then you apply to the number, and if there was a letter, you would also apply to the letter, as long as there's a product of these things inside the bracket. I'm repeating. I'm sure you've seen these SNL in the movies. This stands for sign, number, letter. You apply the exponent to the sign, negative sign. You apply the exponent to the number, get 64. If there was a letter as well, you would apply the exponent to the variable or the letter. Just a reminder. Square root of 4 is 2. Cube root of 8 is 2. Cube root of 8. Remember, this cube root of 8, this is a perfect cube. So you can actually get the answer 2, because 2 times 2 times 2 gives you the 8. Alright, so it's the 2 basically that you get. Cube root of square root of 64 is 8. Okay, because 64 is a perfect square, you get 8 times 8 gives you 64 over 2 minus what's 2 squared? It's 4. Then you get that 4 there. Minus 64, it's 2 times 2 gives you 4 in the denominator. You have 8 divided by 2. 8 divided by 2, guys, is 4. You can apply that, minus 4. Why can I do this division alone and this division alone? It's because it's separated by a plus and a minus sign. And we know that a plus and a minus sign separates our terms. Okay, then you see you get negative 16 plus 4 minus 4. 4 minus 4 is 0. You get an answer of negative 16. So we go back to our options. Which one? What is the value in simplest form of the expression? Is it A, negative 16, B, 16, C, negative 3, or D, positive 3? Guys, positive 3 is out, negative 3 is out, B, which is 16, is out. It's A. Okay. So choosing that option after calculating, please. Guys, for GEC, those who will be writing GEC, you have 2 hours, 30 minutes. The paper is 75 marks. You have more than enough time to make sure that you are spending at least a good 5 minutes per each question. And you are making sure that you are first working out the question. You read the question, you understand what is being asked, then you answer the question first on the side, rough work, then you go and select the correct option. Please, please, please. I know we're only writing in November, but I want us to get into the habit of doing each question. Okay. Let's look at number 7. 4a to the power 12 divided by 4a to the power 3. I'm going to wait for someone to tell me what is the answer in simplest form of the expression. You are not going to spend less than 30 seconds answering this question. Even less than, you're not going to spend more than 30 seconds. You're not going to spend more than 20 seconds. You're not going to spend more than 10 seconds answering this question. Number 7, what is the answer in simplest form of the expression? A to the power 4, A to the power 9b, A to the power 15c, or A to the power 36d. Nice. 123 SVS11. We've got B. Jose, we've got B. Masimbonge Mageba, we've got B. Nice. Okay. I really wouldn't be expecting you guys to butcher this one. Okay, let's not forget that when we divide, the rule is that S and L, we divide the signs. Positive divided by positive is a positive sign. Number 4 divided by 4 is 1. Sorted. Letter, when we are dividing same bases, all right, since this is 12, we are starting with it. It's 12 minus 3, right? Then 12 minus 3, what do we get? A to the power 9. The 1 is there, okay, even though we don't see it, so therefore it's very good. You guys have said it very correctly. It's B. The answer is B. Very nicely done. Give yourself a round of applause, all of you that have actually selected. Let's not forget our exponential laws and the application of those laws. All right. Imagine getting 100% for GEC. How cool would that be? You would be like a pro. Jose, thank you so much for the rosa. You are a pro, bro. Thank you so much. Like, I appreciate the love, guys. It really means a lot. I rarely get it, so when I do get it, it really is such a beautiful thing. I really appreciate it. Thank you. Guys, look at number 8 there. 5 to the power negative 1 plus 6 to the power negative 1 over 5 to the power negative 1 times 6 to the power negative 1. And they are given options there. 60 over 11, is that the answer? B, 11 over 30. C, C is 2, or D, 11. Right. I love this question. Okay. Like I said, guys, laws of exponents. I just want to remind us of our laws of exponents. Law number 1. When the bases are the same and we are multiplying, we add the exponents. Okay. Jose, thank you so much for the rosa. Like, it means a lot. Rosa, Jose doesn't know that it's very rare in my lives to get these gifts, so I really appreciate it. Thank you. Your means a lot. When we are multiplying same bases, guys, remember A is just standing for any natural number or integer. When we are multiplying same bases, what do we do to the exponents? We add them. Okay, that's law number 1. Law number 2. When we are dividing same bases, what do we do to the exponents? We subtract them. You see? Law number 3. If a base is raised to a certain exponent, all right, what do we do to the exponents? We multiply them. Okay. Law number 4. If there are two variables multiplied with each other and they are raised to a certain exponent, okay, let's just say it's P here. So it's A to the power N multiplied by B to the power M. Then each base's exponent, basically the exponent for each base gets multiplied with the exponent that is outside. Okay, so this is like law number 4 in light of law number 3. Okay, and this applies as well, guys, if the relationship between the bases is division. Okay, then we do the same thing. The base at the top gets its exponent multiplied, and the base at the bottom gets its exponent multiplied. Guys, this only applies for when bases are multiplied and when bases are divided. It does not, and it doesn't apply, guys, at all if the bases are added. There's a big mistake that learners do all the time. They think that this thing will apply if the bases are added. You don't. This is wrong. We don't do this, guys. We don't. If there's addition or what? Or subtraction. Okay. This is absolute nonsense. Rubbish. Don't ever do it. Okay? The minute there's addition and subtraction between bases and there's the exponent on the outside, that's when you are able to multiply the exponents. But we don't do it with addition and subtraction of bases. It's wrong. It's nonsensical, right? Don't ever apply it. So I just want to just cancel this out so that you understand we don't do that. Nonsense. Okay. And then lastly, there's this thing here. These two definitions. Definition number 1 says any base raised to the power 0 is equal to 1. That's definition number 1. Definition number 2 has to do with negative exponents, right? And this definition says, okay, I just want to reveal what's here, all of it. Ne? This is like 1a to the power negative 1. So the definition says that if you have a negative exponent, the base that carries the negative exponent moves from the numerator, because at this current moment, you need to understand that this a, I'm revealing, guys, the 1 and the 1. Usually they don't reveal the 1 and the 1. But currently where this base is, it's in the numerator. So you move that base a to the denominator because it has a negative exponent. So this negative causes a to shift its position from numerator to denominator. So it's now here. And then this exponent will change from negative to positive. All right. Then this one is going to be left behind to hold the fort on its own in the numerator. And then you are probably wondering, where is this one? This one is still there, multiplied with the a that basically joined it in the denominator. But you see, the thing is, this one, it usually doesn't show, all right? Because it's there even though it's not shown. And this exponent 1 is usually not shown as well because it's there even though it's not shown. But the 1 in the numerator, we always have to show what is left behind in the numerator, guys, because the numerator has value that needs to be shown. So it always has to be shown. So therefore, we simply say that a to the power negative 1 is 1 over a. Does that make sense, guys? Because that's the definition for negative exponents. If it was a to the power negative 2, the answer would be 1 over a squared. You see, if it is 3a to the power negative 7, the answer is 3 in the numerator, a to the power 7. So this is what we call the application of the negative exponent. So these are just examples where I'm applying the definition of the negative exponent. Okay, so a to the power 0, on the other hand, any base raised to the power 0 is equal to 1. There's only one exception. A cannot be 0. The only exception is that 0 to the power 0 is not 1. It's actually undefined. Okay, 0 to the power 0 is undefined, but in grade 9 we don't really dwell on that, but it's very important to just note. You can even punch it in your calculator. You will see if you say 0 to the power 0, your calculator will say maths error. Okay, so that a to the power 0 will apply for all real numbers, every real number, except a cannot be what? It cannot be 0. That's the only exception. But it will forever, a raised to the power 0, any base raised to the power 0 will be 1 as long as it's not 0, as long as it is not 0. Okay, so these are two important definitions you need to know, additional to your laws of exponents, because when you know these definitions, it's nice. It's paradise. Okay, so let's come to this question, guys. Let's answer this question. I'm going to leave you after this question. 5 to the power negative 1 can be written as 1 over 5. Okay, simply put, what did I just do? I applied the definition. Plus 6 to the power negative 1 is 1 over 6. What did I do? Apply the definition. Over 5 to the power negative 1 is 1 over 5. We can simply apply the definition. Times 6 to the power negative 1 is 1 over 6. Simply apply the definition. So far so good? I hope so, guys. And all you do now is you treat the numerator on its own and you treat the denominator on its own. So I like usually imposing the idea of brackets being there so that I know that I need to treat these alone. And after that, I'm going to divide these two together. Okay, so 1 over 5 plus 1 over 6. I mean, you could use your calculator because remember, in this GEC paper, you are not going to be writing your working out. You are just going to be selecting the right option. Okay, and what you want is the answer at the end of the day. So I hope we can remember, guys, that when we add fractions, what we need to do is we need to find the LCD. So between 5 and 6, we know that the LCD is going to be 30. All right, so what we do is we multiply this by 6. What we do at the bottom, we do at the top. What we do here, we multiply by 5. But what we do at the bottom, we do at the top. So that means we are going to get 6 over 30 plus 5 over 30, which basically gives us 11 over 30. So I know that in the numerator here, I have 11 over 30 here. Okay. Then what about here in the denominator? What's 1 over 5 times 1 over 6? With multiplication, it's straightforward. I can just simply multiply 1 times 1 is 1, and then 5 times 6 is 30. So that means in the denominator, I'm going to get 1 over 30. Okay, then from there, what do? I'm going to divide 11 over 30 divided by 1 over 30, which is the same thing as what? If I change the division sign to multiply, what happens to my second fraction as per the rule that I know? Change divide to multiply, my second fraction becomes 130 over 1. Then what happens? 30 goes into 30. I can cancel those two because 30 divided by 30 is 1. So I can then now multiply 11 times 1 is 11. 1 times 1 is 1. And then 11 over 1 simply means my answer is 11. Okay. Okay. Nicely done. Nicely cooked. Okay. That was cooked nicely. All right. I would advise you that when you do get the chance and you are actually watching the video again of the replay in my YouTube channel, you can always just slow it down. You can press you can say times 0.5 so that you can hear me speak very slowly to get to the answer. Okay. Yeah. Okay, so we would answer. What is the answer in simplest form? It's D. Our option there would be D. D, D, D. Done. Right. Sure. Oh, that was cool. Even if I must say so myself. Right. Okay, guys, I'm gonna leave you with these to do, and then tomorrow morning, okay, I have to go now. Tomorrow morning, when we meet again, I'll be picking up things at number 9, right, and we'll be continuing from there. We still have all the way up until like 30 something or 40 something, I think, but this is the beginning. All right, and I'll be doing GEC papers every morning coupled with maybe some other mornings with just other past question papers from various provinces, paper 1, paper 2, so that you can start revising these papers with me every morning before you guys head off to school. Thank you so much. I hope you guys have a great and amazing day, whatever you may be doing at school. Guys, if at school right now, maybe there are a lot of things being done. There's a lot of activity happening. I know valedictories are happening. Grade 12 valedictories are happening. Maybe a lot of focus or attention may be turned to the grade 12s. Teachers may not really be in classes at the moment and so forth, but do not be despondent. Remind yourself. I will definitely remember Jose. Thank you so much as well for that, Jose. Guys, remember your own personal goal. You know what you want. Some of you in grade 9 want to actually go and do pure maths next year. So that means your maths marks need to be, A-okay for this term. So please, guys, make sure you do join in the mornings when I do have these live lessons for grade 9s. And like I said, starting at 5 a.m. as early as 5 a.m. I'm hoping to actually start as early as 5 a.m. 10 past 5 in the morning, so that we can have a full-on time together in the mornings and actually really get the maths into the system. So thank you so much. Have a great day and lots of love to you guys. Remember, maths is a game. We play, and we level up. That's what we do, guys. That's what we do. Cheers.